Hey guys, it's Professor Tiffany Martin with Medical Microbiology, and we are working our way through Chapter 5. We've just talked about redox reactions. We talked about metabolism, anabolic, catabolic reactions, and we are now need to talk about enzymes. Before we can get to the nitty-gritty of cellular respiration, we need to know what an enzyme is and what it does. So I think you have some familiarity, so this will probably go by pretty quickly. If you need to stop and review anything, please do. But otherwise we're going to try to zip through at least the beginning of this. Okay, so let's see. Here's your fill in the blanks. I will stop for a minute and see if you can fill in this page. Okay, how'd you do? Enzymes determine the metabolic activity of the cell, which just means what can they do? Can they break down glucose? They need an enzyme to do that. Can they break down fructose? They need an enzyme, that representative pathway that we talked about. There are things that are going to make these reactions happen. So that's what it's just saying. It determines the metabolic activity of a cell. If it has an enzyme, it can do something. If it doesn't have that enzyme, it can't do it. The enzymes are proteins, so they are programmed in our DNA. So they are heritable characteristics. As such, when you have a bacteria or microorganism or any organism, whatever enzymes they make can be passed down to their progeny. So we can use these for categorizing, differentiation, naming organisms. Sometimes they're named based on different enzymes. So that's what we use a lot for that. They're heritable characteristics. We can block enzymes. And this is when I gave you that project as a drug, manufacturing a new drug. And if we had a biochemical pathway and we wanted to disrupt it, this was a pathogen that had a pathogen's biochemical pathway, and we wanted to harm the pathogen without hurting the host. So I said, where would you do that? Well, enzymes are very good targets for that. So they can be bound to agents, chemicals like drugs, antibiotics, and then shutting down that biochemical pathway can inhibit bacterial from growth. And as we go through and we talk about bacteria, depending on what the bacteria does, can have a lot of practical applications for us. And we've already seen that with Pasteur and the French wine industry, right? Yeast had the ability, had the enzyme to take sugar, grape juice, and turn it into alcohol. Well, we have found a practical application for that. And then we'll talk about some others too as we go through the course. Okay, I'll give you a second. Try it. Do it. Okay, so let's talk about characteristics of enzymes. I've already mentioned they were proteins. Some of you got that. And so as such, you know, a protein folds into a specific 3D shape. So it has a specific shape, and that's going to be important with how it interacts with things. We consider enzymes organic catalysts that speed up chemical reactions by lowering the energy of activation. So enzymes lower the energy of activation, and this is a catalyst from that. So when I'm talking about that, and I think I have a when I'm talking about that, an enzyme will bind to a substrate, and then it will do something to that substrate. Maybe it's going to break it apart or something. So the enzyme binds to the substrate, acts on that substrate does something, you know, breaks apart or whatever. And now that substrate, if it can break apart, occasionally it will. Spontaneously, it's going to break apart, but statistically that's going to be a very small percentage. It's not going to happen very often. But if an enzyme binds to it and breaks it apart, well, now we've got something going on. Think about like a package of cookies. You know, I'll get a package of cookies and there'll be one that's broken in there. Occasionally, every third package, I'll have a broken cookie. But if I stomp on the package, then I can break the cookies and then I'll have a lot of broken cookies. The enzyme is going to catalyze a reaction, and it does that by what they call lowering the activation energy, making it easier to break that apart. All right, so that's what an enzyme does. It's an organic catalyst. An enzyme is like a tool once it breaks apart a protein or whatever molecule it's working on, then it goes and looks for the other one. And we talked about that when we talked about that representative metabolic pathway, that if we are going from molecule A to molecule B and we need enzyme 1 to do that, enzyme 1 is going to always bind to A, and every time it binds to A, it's going to turn it into B, and then enzyme 1 gets released and it's looking for another A molecule again. So you can think of it like a tool. You know, if you're hammering a bunch of nails, you need a bunch of nails, but you only need one hammer to do that. So they're not used up, they're not destroyed when during their work. They are recycled and used over and over again. So keep that in mind. Okay, so this is that chart when I talked about the catalyst and the activation energy. Here's what we're starting with. This is our reactants. We want to get to this. It's a product here. Now, it will happen eventually, but it's going to take a lot of energy to do that. But if that enzyme binds it, it lowers that activation energy from that. So that's how enzymes work. Okay, you got another one. Go for it. See how you can do. Okay, so specific in action. They react with only one particular substrate, and we mentioned that as well. Enzyme 1 only binds to A and takes it to B. If we go back to that representative metabolic pathway. Do you have your notes out in front of you? Can you refer back to that? It would be helpful. All right, so specific in action reacts only with one particular substrate. So enzymes are specific, and we said when we were doing alternative pathways that we couldn't make enzyme 1 do something different. Enzyme 1 only bound to A and turned it into B, so it's very specific. Substrate is just a vocabulary term. A substrate is what binds to the active site. And let me show you, I drew that one out on my thing. So if this is my enzyme here, it is a protein, it's in a specific 3D conformation, there's going to be a place within that protein on my Pac-Man enzyme here that's going to bind to a molecule. This molecule has a proper name. It may have a name in the pathway. It may be the precursor or one of those intermediates, but it also has a name in relationship to the enzyme. So it's called a substrate. A substrate is a general name for any molecule that's going to bind, that the enzyme is going to bind to. So substrate is the name of the molecule. A general name for it. It's going to bind to the enzyme, and where it binds, where it actually comes in contact with it, is known as the active site. So that helps you understand that. So now when the enzyme and the substrate bind, we actually, kind of fit. So you can kind of see that this substrate is going to fit perfectly right into this active site. And we can kind of call that like a lock and a key. You know how you need a different key for every single lock. It's very specific in nature. And that works, but I also want you to think about it as kind of a magic key, a Harry Potter key, a cartoon key. If you can think of a cartoon where where you're going to put the key in the lock, and when it does that, like the lock is going to change and like meld to the key. That's called an induced fit. And that's what happens when I have my Pac-Man enzyme and I have my substrate. When they come together, Pac-Man kind of gobbles it. It kind of melds to it. And that's called an induced fit model. So let's go back to this and fill that in. So it's going to bind to the active site and it's going to fit like a lock and key, but do remember that it's a magic lock and key and you get that induced fit. Enzymes are heat sensitive. Remember, they're proteins, so if you raise up the heat, they are going to denature from that. They are also sensitive to pH. You know this because you've cooked eggs in the morning. You crack an egg on the and the protein, the egg white, is going to change when you heat it. It's a permanent change. When you cool down the eggs, you don't get that egg white to come back. It is a permanent change. So enzymes are denatured, and they're also pH sensitive, and that also will denature enzymes. And you know this because of pickles. If you put a cucumber in a acid of vinegar, then you can turn it into pickles. So that is also something that you know. All right, so this is a picture, and this is going to show you my locking key and the induced fit. There's my substrate, there's the enzyme, there's the active site, and you can see how that enzyme kind of melds to it. Now, do remember this is just a 2D representation, or actually I guess it's more of a 3D drawing, but these are proteins, these are molecules, and they will bend and show that. So that's just a little bit more about that, okay? Okay, so this picture is a fancy picture, and it has all those big names that we're scared about, but we are not going to be scared about these big names because we're just going to give them names in relationship to one another. Here is the enzyme, here is the substrate. Now that substrate has a proper name. It's actually fructose 1,6-bisphosphate based on the elements that make up this structure. The enzyme has a proper name. It's fructose 1,6-bisphosphate aldolase, and we'll talk about how we name enzymes in a minute. But we're going to see how that enzyme binds. When that enzyme binds, you notice that induced fit and that change in that conformation. When they do bind, this is called the enzyme substrate complex. The enzyme's going to do something to this. In this case, it breaks it apart into glyceraldehyde 3-phosphate, dihydroxyacetone phosphate, and then the enzyme you can see comes off and it's ready to find another fructose 1,6-bisphosphate. So again, don't let those big words scare you. Look at the relationships and understand what is going on. This is actually an enzyme that's in the process of glycolysis, which we'll talk about in a little bit, but don't let the big words scare you. Okay, so let's do cofactors really quickly, so take a minute. Okay, how many could you fill in? Let's work through and see where your holes are. Cofactors are necessary to activate some enzymes. Some enzymes can work just fine by themselves. Some are going to need some help. And if they need help, the help is a molecule that we refer to as a cofactor. Cofactors can be in two categories. You can have inorganic cofactors, which are metal ions, or you can have organic cofactors, which we can also call coenzymes. These are things, so the enzyme is a protein, it's heritable. We have a DNA, we have instructions for that. Cofactors we don't have instructions for. We cannot make them, or the bacteria cell cannot make them. These are things that we're going to have to acquire in our diets. These are our vitamins and minerals. So our inorganic cofactors, these are the metal ions. These are our minerals from our diet. Can you think of some? Zinc, copper, iron, magnesium, any things of those nature. Those are minerals. And they work, and I will show you this, by forming a bridge between the substrate and the enzyme, and it's based on charge. So a cofactor will come in and bind to the enzyme. So this red piece right here, this is my inorganic cofactor. It's copper, magnesium, something here, and it's going to fit in with this enzyme. It's got a place where it's going to fit. It has a charge, and it's going to interact with the substrate, and the substrate is going to have an opposite charge, and that is going to facilitate this interaction. It helps that enzyme to bind to the substrate. So that's how inorganic cofactors work. If this enzyme needs a cofactor to work, it's going to always need that cofactor, okay? Which is why it's so important to get the right vitamins and minerals in our diet. If these cofactors are necessary for this enzyme to function, they're always going to be necessary. Okay, so let's look at organic cofactors, which we also call coenzymes. They work a little different. They are organic, which is why we can also label them coenzymes. And they are going to, these are your vitamins, and they work a little differently. They actually complete the active site of the enzyme. And they're also going to be important with carrier molecules. So let's go back to my little drawing here, And this time, this particular enzyme, I've switched it up. This is a different enzyme, a different substrate. And you can see the substrate and the enzyme, it doesn't quite fit. The enzyme by itself, this is the protein that was encoded in your DNA and you made it, or the bacteria, it doesn't really matter, it works the same. Here's the enzyme, is not fully functional. It needs a coenzyme. It needs an organic molecule that's going to bind with your enzyme, and it usually completes the active site. Now you can see, I should have used a different color besides blue, but this coenzyme here, this organic cofactor or coenzyme, binds to the enzyme that we made, and it completes the active site. Now the substrate can bind in there, then you can have him. So if we do not get our cofactors in our diet, we get diseases like rickets, vitamin D deficiency. You've got diseases from that. These are also going to be important when we start talking about that. Some of these coenzymes are excellent at oxidation and reduction. Remember those redox reactions, oxidation and reduction? Some of these coenzymes are really good at accepting electrons and donating electrons. And we're going to use that in parts of cellular respiration. And so I can edit the video and I can save it if I can get out of it.
Hi, Professor Martin's microbiology class. I know that she's not the best at technology, but she tries, so just love her.
What do you think I should push?
I don't know.
I know, right? I even hit the dreaded escape.
You might have to turn your computer off and then turn it back on again.
I'm scared. All right.